So now we're getting into a new chapter, which is about gases. Right there, chapter 5, gases. Um, some background about gases. They take the shape of their container, unlike solids and liquids. Well, liquids will take the shape of not the complete container, just the lower half of the container. And solids just sit wherever they are. The gas phase is the most compressible state of matter. To compress is to push down, so we can make gases smaller, compress them. But I have a little side note here. This is not just about gases, but most of these elements are gases, and you need to know this fact for now on. Hofbrinkel, these are the 7 diatomic molecules. When you have pure hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, or chlorine, they are diatomic when they're at 25 degrees Celsius. So the standard state for these elements, and we just say Hofbrinkel, their standard state is to have 2 atoms covalently bonded. All right, so gas pressure. Pressure, when we talk about gaseous pressure, that's caused by gas particles hitting the walls of their container. The harder they hit their walls, the higher the pressure, and the more molecules that hit the walls, the higher the pressure. As the number of collisions and or the force of the collisions increase, pressure will increase. So if you increase the number of gas particles, you'll have more collisions. If the particles are moving faster, then the force of those particles hitting the wall will increase. And these both have an impact on the pressure. Units for pressure, we have a bunch of different units. You won't have to memorize these conversion factors. We can convert between any of these units. And all of these units can be abbreviated. And you should write down those abbreviations. So ATM is atmospheres, TORR is torr. MMHD stands for millimeters of mercury, literally the element mercury. It's how high mercury goes, and you'll see that in the measuring pressure section in a moment. kPa, kilopascals, psi, pounds per square inch. Now we measure pressure using a manometer or sometimes a barometer. You might hear the barometric pressure when you're listening to the radio. And you should note that the dark area here, which ends right there, that would represent mercury. So when we talk about millimeters of mercury, we're talking about how high mercury gets pushed by either atmospheric pressure or by a gas. And you should make a note here that this manometer is a closed manometer. Notice it's closed right there. And the latter two are open manometers. So see how these are open to the atmosphere. Those are open manometers. Now the pressure of this gas here would just be this height. It's how high the gas is pushing the mercury up. And in here there would be a vacuum, so there's no pressure in here. This pressure in here is 0. So the gas pressure would be the height in millimeters of mercury. That's what millimeters of mercury means. Over here you should note the gas is pushing harder. Notice it's pushing the mercury lower than the outside air. So air pressure is pushing on this side, and the gas is pushing on this side. So the gas pressure will be the outside pressure plus this distance, because the gas, you have to look at the manometer to see which side is pushing harder. So here the gas would have the atmospheric pressure plus the height. And then here, who's pushing harder, the atmosphere or the gas? Who do you think? Hopefully you said the atmosphere is pushing harder, because you can see the mercury is lower on the atmospheric side versus the gas. So this atmospheric pressure pushes more than the gas. So the gas pressure would be the atmospheric pressure minus this height. Okay. So let's do some practice just converting the pressure units. We're going to use these conversion factors up here. We want to convert millimeters of mercury to atmospheres. So that's all showing right there. Okay. So 26 millimeters of mercury, we had the conversion up here. That's 760 millimeters of mercury equals 1 atmosphere. We can convert between any of these two. We don't have to convert from millimeters mercury to torr to atmosphere. Students sometimes make that mistake and spend too much time on the problems. We go straight from millimeters mercury to atmospheres. And if you do this on your own, you should get the numbers you see here. And why did I keep only 2 digits here? Because of sig fig. So sig fig, sig fig. Okay, pause and try this one on your own. Make sure you're pausing. I'm going to show you the answer, but you should pause the video while you do this on your own. There's your answer. Why did I keep 3 digits? Because there's 3 digits in the question, so I need to keep 3 sig figs. For multiplication and division, we keep the smallest number of sig figs in the problem. The problem had 3 sig figs. Alright, there are a bunch of gas laws, and they have different names. The first gas law we'll look at is Boyle's law. And Boyle's law tells us that pressure and volume are inversely proportional. As volume decreases, pressure increases. Next law, Charles' law. Charles' law says that volume and temperature are directly proportional. So as temperature increases, the volume of a gas will increase if pressure is kept constant, if the other variables are kept constant. Also, when we do temperature with gases, we always have to have the temperature in degrees Kelvin, which is different from Celsius. Kelvin is equal to Celsius plus 273. We always have to remember this is very important. Don't forget this. And the last law is Avogadro's law, which says that volume and moles are directly proportional to one another. All right, and we can use these 3 laws to get the ideal gas equation, which is PV equals nRT. This is a very important equation. That's why I wrote it in red. The P right here is pressure, V is volume, N stands for moles, R is the universal gas constant. You'll see what that is in a moment. It's a constant, and T is temperature in Kelvin. Note temperature must be in Kelvin, and I'm having you write this again, so you try to memorize that Kelvin is Celsius plus 273. And then the universal gas constant, what is that? It's just a constant. It's got 4 different units in it. When you do problems, you want to write down all your units. These are just units, not numbers, just units. Okay, so here's a problem that I should have covered this part up for you, but I didn't, so we'll just look at that now. So what mass of nitrogen gas is in 2.5 liters at 52 kilopascals and 25 degrees Celsius? So you look at all of the data that you have and you figure out what information are they giving me. That's how you figure out how to problem solve. So I've got 52 kilopascals right there, kilopascals. And you should recognize that that's a pressure unit. You're going to have to get familiar with these different units right here, these right here, and recognize that those indeed are, Control Z, those are pressure units. Okay, where did we go? There we are. So 52 kilopascals. We are going to convert those to atmospheres, the units of atmospheres, because the gas constant has atmospheres in it. Okay, and then, so we want the pressure in atmospheres because the universal gas constant has atmospheres in it, so we always want our pressure in atmospheres if we're going to use the ideal gas law and the gas constant. Okay, another data point we have in here is our 25 degrees Celsius. You should recognize that's a temperature. And what do we have to do when we have Celsius? We have to convert to Kelvin. So we had 273 to get this number. And let's see, we also have 2.5 liters, and you can identify that's a volume. So now we've got volume, temperature, and pressure. And we look at this right here. If we have volume, pressure, and temperature, we could get moles. So you look at that and you say, oh, I can use the gas law to get moles. The question asked me for mass, so I can find N from the gas law, and then I can just convert moles to grams. You can pause, try that on your own. I'm going to put the solution up. So I always like to isolate N or whatever variable I'm trying to solve for. So I don't just plug numbers into the ideal gas law, I isolate the unknown, which is our moles. So isolating n, we get n is PV over RT, then I plug in all my values, PV over RT, solve this whole equation. You should always check your units to make sure they cancel. They will cancel. We will end up with moles. And the reason why moles are in the numerator over here is because this whole fraction here is in the denominator, and we have to invert it, which puts the moles on top, to get this fraction out of the denominator. So we get our moles of nitrogen. And Hofbrinkel. Remember how I mentioned Hofbrinkel a little earlier? You should recognize that nitrogen is part of Hofbrinkel, the in Brinkel. So this is diatomic. When we convert to grams, we have to use the molar mass of 2 N's. 28 grams per mole, we get 15 grams of N2. Why did I keep only 2 sig figs? Oh, right here, the pressure is 2 sig figs. You should notice with temperature, we actually end up having 3 sig figs, even though we started with only 2 because of our addition-subtraction rules. All right, and next question. What is the temperature of blah, blah, blah? You can read. You should pause this. Again, try it on your own. Identify what the variables are. These grams of oxygen will get you to moles, so you find moles. This will give you your volume. This will give you a pressure, and you have to do all your conversions. I'm about to show the solution. Okay, so our grams of oxygen, we solve for moles, because we're going to use PV equals nRT. Our volume, well, why did I convert to liters? Can you figure out why? Right here, the gas constant, the volume unit is in liters, so I have to make sure that my volume in the ideal gas law is liters. Pressure was given in millimeters mercury, but I need to convert that to atmospheres because the universal gas constant, it has atmospheres in it. So, as in the previous example, we want to isolate the unknown, which is temperature. So isolating T in the ideal gas law gives you T as PV over nR. We plug in the variables to get 298 Kelvin. And the question did not specify what units they wanted the temperature in, so we can just leave this in Kelvin. All right, there are other kind of gas problems. They're called two-state problems. And in two-state problems, they're called two-state because we have a gas starting in one set of conditions, and then those conditions change to a second state. It's still the gas state, but it's a different set of conditions. So we have a gas. You know you have a two-state problem when you see the variables P, V, N, or T, any of them twice. You know you have a two-state problem. So we have a temperature and a volume, and a new temperature and a new volume. Notice volume was twice, temperature was twice. We're dealing with a two-state problem. Let's identify what all of our variables are. First, we have 25 degrees Celsius, and the gas was at 25 degrees Celsius, so that would be our initial temperature. And that gas is in 2.5 liters. So it's at 25 Celsius in 2.5 liters. That's our initial volume. Note, I changed the temperature to Kelvin. You have to always change temperature to Kelvin. Don't forget that step. What is the new temperature if the volume is increased to 50 liters? So we're increasing the volume. That's our new set of conditions. That would be V2, 50 liters. And we do two-state problems a little bit differently from ideal gas laws. First, you write the ideal gas law. Oh, we want to know what the new temperature is. Okay, so we write out PV equals nRT, and we're going to underline the variables that are in the problem. Well, our variables are volume and temperature. It's hard to see this because Word does its automatic little, it doesn't like the semantics here. Things, I've got this misspelled. Anyway, the T is underlined and the V is underlined. So I'm going to rewrite the gas law with just the underlined variables. So I will write V equals T. We rewrite the ideal gas law with only the underlying variables. We will write just V equals T, and I'm going to put 2's. I'm going to put 2's on there. So I put a subscript 2 on the variables. V2 equals T2. And then I divide by the same variables and write a subscript 1 on the denominator. So V2 over V1 equals T2 over T1. I'm going to make that. Okay, there, so you can see it better. So we write only the variables that are in the problem, which were volume and temperature, and we'll notice they're on opposite sides of the equation here, so I write them on opposite sides of the equation. I write subscript 2 in the numerator, and then I write subscript 1 on the denominator. And then I just isolate the unknown. The unknown is T2. If you isolate this for T2, what do you get? Isolate the unknown, plug in the numbers, solve. You get T2 is V2 T1 over V1. If you didn't get that, you should try that on your own. Try to isolate everything on your own and see what you get. And then you plug in your values and you get this right here. You get 596 Kelvin with your T2, but I can only keep 2 sig figs. So I have to rewrite that as 6.0 times 10 to the 2 Kelvin. All right, last problem. A gas is in 250 milliliters at this is a pressure unit, and then we increase to a new pressure unit. We want to find a new volume. So notice I've got volume twice, pressure twice. That means I've got a two-state problem. So what do I first do? I write the ideal gas law. Oh no, I identify my variables. And why am I converting one pressure into the other pressure? So with these, I don't have to convert both pressures to atmospheres because I'm not using the gas constant. I'm just identifying my variables, and then I see it's a two-state problem because I've got pressure twice. And I need to have the same pressure. I just chose to convert the millimeters mercury to kilopascals. You could have converted kilopascals to millimeters mercury. So identify all your variables, do whatever conversions you'll need to do, and then we write the ideal gas equation underlining the variables that we're going to need to use. So this time we only need P and V. Now that one looks weird because I'm going to get rid of all these. If I get rid of everything, it doesn't become 0. So if I write P2 V2 over P1 V1, because remember I divide the gas law by itself, with just the variables that we're showing, I get that that is equal to 1. So P2 V2 over P1 V1 equals 1, because nRT over nRT will just be 1. Isolate the unknown. What's the unknown? Let's see, we must be missing V2. What is V2? The new volume. So we're going to isolate V2. You should pause and do that on your own. And hopefully you got this. P1 V1 over P2, plug in our values, keep the right number of sig figs, and you get 168 milliliters.